Okay, so we multiplied those two polynomials together, and it looks like we get our final polynomial is x to the fourth minus 2x cubed plus 6x squared minus 2x plus 5. So this is the polynomial with the zeros specified. Now I want to just show you that you can use synthetic division with complex numbers also. So here's the 1x to the fourth, negative 2x cubed, 6x squared, negative 2x, and 5. So you can put an I in here, bring down the 1, multiply by the I, you get I. Add those, you get negative 2 plus I. Then multiply by I, and you get negative 2I plus I squared, which is minus 1. So you add that to 6, and you're going to get 5 minus 2I. Multiply by I, you're going to get 5I minus 2 times I squared. So that's going to be plus 2. Add, and you get 5I times I, which is negative 5, and add, and you get 0. So you can do a quick check and make sure that I really is a 0 of this polynomial that we just created. So here's another useful theorem, and this is about factoring over the real numbers. So every polynomial function with real coefficients can be uniquely factored over the real numbers into a product of linear factors and/or irreducible quadratic factors. So notice the difference between this and the earlier theorem. The earlier theorem said that every complex polynomial can be factored all the way down to linear factors. So it makes a big difference if you're going to real only over the real numbers, looking for real zeros. You either get linear or irreducible quadratics, and those are ones where you would get complex solutions like x squared plus 1. If you're going for complex zeros, then you can always go to linear factors, always. Okay, so here's an example where you're supposed to use the given 0 to find the rest of the zeros of the polynomial. And we'll do one here, and then we'll do another one in class. So if I have a 0 of 5, negative 5i, then I also know I have a 0 of 5i. So I know that x plus 5i is a factor, and x minus 5i is a factor. Let's think about this. If I have the number 84, and I know that 6 times 7 is 42, and I know that 42 is a factor of 84 because 42 times 2 is 84, then 6 has to be a factor of 84, and 7 has to be a factor of 84, and 6 times 7 has to be a factor of 84. So my point is that if this is a factor of the whole polynomial, and this is a factor of the whole polynomial, then their product, x squared plus 25, also has to be a factor of the polynomial. So let's divide x squared plus 25 into this polynomial and see what the other factor is. So I have x cubed plus 3x squared plus 25x plus 75. Multiply by x, I'm going to get x cubed plus 25x and subtract. So that's going to leave me with 3x squared plus 75. And I have plus 3, and I get 3x squared plus 75, and subtract, and I get 0, which is good, because that means that x squared plus 25 divides evenly into that polynomial. So I get x squared plus 25 times x plus 3. And this is how you could write g of x. So you can see that the other 0 is x equals negative 3. So the remaining zeros, make sure you answer the question. The remaining zeros are 5i and negative 3. Okay, and we'll do number 30 together in class. Okay, so when we're finding complex zeros, then we need to go all the way down to linear. So here's one that's your worst nightmare if it was on a test, so I guarantee you it won't be on a test, but it's a good take-home test problem because you're going to have to start with, oh, I don't know, I have factors of negative 52 over factors of 3. There's a lot of them. Plus or minus 1. 2 goes into 52, so I'm going to have plus or minus 52 and plus or minus 26. 3 doesn't go into 52, but 4 does, and 13 does. And that's it. So then that's over plus or minus 1 and plus or minus 3. So it could be a fraction, but let's hope that it's an integer and just try some synthetic division. So I usually do it systematically, and I'll try 1. So that didn't work. I have a remainder. So let me try negative 1. That didn't work either. So you just keep trying until you find one that works. So let's try 2. That's not going to work either. How about negative 2? Well, that's not going to work either. So I'm thinking it's a fraction. So let's try 1/3. See what we get. Yay! So if we have a remainder of 0, it means x minus 1/3 is a factor. And the other factor is, this is constant, x term, x squared, x cubed. The other factor is 3x cubed minus 9x plus 156. But if we're asked to factor over the complex numbers, then we know we have to get down to all linear. So let's try some more. If we have 3, 0, negative 9, 156, we can start over again with, let's see, if 1 wasn't a factor of the original polynomial, though, then it's not going to be a factor of this depressed equation either. So let's try negative 1/3 and see what happens. So we'll have 3, negative 1, 1/3, negative 26/3. That doesn't look like it's going to work. So let's see, we also have 13. What do you think? Is 13 going to work? I have 3, 39. That's going to get gigantic. So we'll figure out the rest of these in class together, but I wanted to at least get to this point so that you can see how to get started. And then we'll do this other problem here, number 38, in class together. And that's it.